Hello and welcome back to stats. So hopefully you're ready for the next section, which is section 1.2. So again, we have some more PowerPoint slides to go through, so we'll kind of walk through those and hopefully your questions will be answered. So let's start. So we have 1.2, which is going to be on types of data. And so a major use of statistics is to collect and use sample data to make conclusions about populations. So again, that kind of boils back from what we saw in the first section. So again, we're looking at sample data to kind of describe what's happening with the bigger population. So this is just a reiteration of that conclusion. So now some more terms that we're going to be looking at. So parameter is going to be the first one, a numerical measurement describing some characteristic of a population. So again, easy way to remember it, P and P, parameter, population. Similarly, we have statistic, a numerical measurement describing some characteristic of a sample. So same thing, S and S. Statistic and samples go together. So now I just want to do a quick little example from the textbook. So if you're looking at your notes, I have example 1 on page 14. So let's just flip over to there real quick. So here we are. So if we scroll down a little bit, example 1 says there are 17,246,372 high school students in the United States. In a study of 8,505 U.S. high school students 16 years of age or older, 44.5% of them said that they texted while driving. No. At least once during the previous 30 days, based on data in texting while driving and other risky motor vehicle behaviors among U.S. high school students by Olson, Schultz, Eaton Pediatrics, Volume 131, number 6. Okay, so there's some information. So now let's break it down. So the first thing is the parameter. The population size of 17,246,372 high school students is a parameter because it is the entire population of all high school students in the United States. So again, all of that particular group is represented by that 17 million figure. So if we somehow knew that the percentage of all 17 million high school students who reported that they had texted while driving, that percentage would also be a parameter. So again, if you're pulling information from a parameter, you're still dealing with parameters. On the other hand, statistic, the sample size of 8,505 surveyed high school students is a statistic because it's based on a sample, not the entire population of all high school students in the United States. The value of 44.5% is another statistic because it is also based on the sample, not the entire population. So again, it's pretty cut and dry, but you just got to make sure you keep those two terms straight. So, all right, let's move on. We have quantitative data. Quantitative or numerical data consists of numbers representing counts or measurements. So another way to think of it is quantitative has the word quantity in it. So if you have a quantity of something, you have a specific amount of something, a numerical amount of something. So example, the weights of supermodels, the ages of respondents. So all numbers. On the other hand, we could have categorical or qualitative data, and that consists of names or labels, not numbers that represent counts or measurements. So again, names and labels. So it has a quality to it, but it doesn't have a quantity to it. So that's kind of a way you can keep those two terms straight in your head. A couple of examples, the gender, male, female of professional athletes, shirt numbers on professional athlete uniforms, substitutes for names. So that's kind of a tricky one because, if you see numbers, again, you're thinking quantitative data. But because it's a shirt number, really the shirt number is a substitute for the name of the player. So you really can't do anything. It's not measuring anything, those numbers. So that's the key. If it doesn't measure something, then chances are it's not quantitative, it's qualitative. So that's definitely something to be careful about. So we like working with quantitative data because it's numbers and you can do more stuff with it. So quantitative data can be further described by distinguishing between discrete and continuous types. So a discrete result when The data values are quantitative and the number of values is finite or countable. So countable is probably the safer way to describe discrete. So if you can count it, it's discrete. So example, the number of tosses of a coin before getting tails. So that's a finite number and it's a countable number. On the other hand, we have continuous data that results from infinitely many possible quantitative values where the collection of values is not countable. So be careful. So C and C don't go together in this one, continuous and countable. It's just the opposite. So for example, the lengths of distances from 0 centimeters to 12 centimeters. So you could have an infinite number of choices between 0 to 12. That includes all decimals and things like that. So that's another, identifying feature of continuous data. If it's got a decimal value onto it, 0.5823, something like that, that means it's continuous. It's not a, countable number. So I have in my notes, if I look at it correctly, that we have a couple examples from the textbook again. So let's flip back to that. And we got to go to page 23. So let's go to 23. Oh, there it goes. All right, and 13 and 15. So let's scroll down. Okay, so the question says, determine whether the data are from a discrete or continuous data set. So 13 says, the freshman 15. In a study of weight gains by college students in their freshman year, researchers record the amounts of weight gained by randomly selecting students, as in data set 6, freshman 15, appendix B. So what would that weight gain be considered, do you think? Would it be discrete? Is it countable? Or is it continuous and it's not countable? Okay, so I won't do that. Hopefully you're guessing it's countable. It's not countable, which means it's continuous. So if it's going to be continuous, again, you're not going to gain, I want you to gain exactly 3 pounds. There's no way that can happen. So that's got to be a continuous variable. So let's look at the next one. McDonald's. In a study of service times at McDonald's drive-up window, the number of cars serviced each hour of several days are recorded. So what would the number of cars be considered? Yeah, you guessed it. It's going to have to be discrete. You have to have a specific number of cars. You can't have a half a car go through. So that would have to be discrete. All right. So far, so good. So let's see what's on the next set of slides here. So now we can go even further. Levels of measurement. Another way of classifying data is to use 4 levels of measurement: nominal, ordinal, interval, and ratio. Oh boy. All right, so let's start with the most generic. The most generic would be the nominal level. So it's characterized by data that consists of names, labels, or categories only, and the data cannot be arranged in some order, such as low to high. So again, it doesn't matter what order they're in. It doesn't make any real sense to put it in one way or another, but names and labels and categories only. So pretty much you can kind of classify that as qualitative data or categorical data. So example survey responses of yes, no, and undecided. It really doesn't matter what order those 3 choices are in. It doesn't make it better or worse. So that's why it's nominal. The next step up from that would be ordinal. Ordinal level of measurement involves data that can be arranged in some order, but differences obtained by subtraction between data values either cannot be determined or are meaningless. So again, we're probably dealing with categorical qualitative data still, but now we can put it in some sort of order, and it makes a little bit more sense. So what's the example we have here? Course grades A, B, C, D, or F. So you don't want to mix up the order of that. It doesn't make as much sense. It's better to keep it in nice, clean order like that. So that's ordinal. The next step up from that would be interval. It involves data that can be arranged in order, and the differences between data values can be found and are meaningful. However, there is no natural zero starting point at which none of the quantity is present. So now we're talking about quantitative data. So we're talking about numbers primarily. when we're talking about interval level of measurement. So what's our example here? Years, 1000, 2000, 1776, 1492. So we can calculate differences. We know how far apart they are mathematically, but is there a zero starting point? Is there, zero starting point of time? Well, technically, yes, but we don't have it starting at, the beginning of time because we're not 100% sure when that is. We have a pretty good guess, but we don't know exactly. So that's why this is interval. There's no natural zero starting point. The last one is ratio, and so it keeps building up. So we can put them in order. We can find differences between them, but now there is a natural zero starting point where none of the quantity is present. So class times of 50 minutes and 100 minutes. You could have a class time of 0 minutes. You can't really have a class time of negative time. That wouldn't make any sense. So 0 is the smallest one. It doesn't have to be part of the examples that they give, but you just have to realize that for this for this quantity that you're looking at, 0 would be the lowest that you could possibly get. So that's why it's ratio. So to summarize, we got nominal, categories only, and again, no order. Ordinal, categories with some order. Interval is differences but no natural zero starting point. And then ratio has the differences and a natural zero starting point. So remember, interval and ratio, you could also put in there that it's quantitative. So again, we're talking about numbers. All right, so looking at the notes again, we got some more examples to help clarify that. So let's flip back over to the textbook right there. And we want to go to page 24. So let's go to 24. Here we go. Number 23. So the directions just say to determine which of the 4 levels of measurement, nominal, ordinal, interval, ratio, is most appropriate. I'll get it out. So M&Ms, colors of M&Ms, red, orange, yellow, brown, blue, green, listed in data set. So what do you think on that one? Well, we're not talking about numbers, so that kind of restricts it down to the first 2 choices. It's either nominal or ordinal. So nominal means no order. Ordinal means some order. So does it really make a difference what order those colors are in? Not really. So this is going to have to be nominal. It's going to have to be nominal. It doesn't matter what the order is, and we're talking about categorical data. Okay, so let's look at 25. Baseball statistician Bill James records the years in which the Baseball World Series is won by a team from the National League. So what's the data we're looking at? They're looking at years. Well, we kind of already had an example about years, right? So we're talking about numbers, so that means it's either interval or ratio, but is there a zero starting point for years? No. So in this case, it's going to have to be interval. All right, let's try number 27. Lead in blood levels of low, medium, and high are used to describe the subjects in data set 7, IQ and lead, appendix B. So low, medium, and high. Well, it's not numbers, so that means it's either nominal or ordinal. So does it make sense to have some order to it, or does it really matter? It probably makes more sense to put them in order, low, medium, and high, or high, medium, and low. So I would say that should be ordinal level of measurement. All right, so hopefully that kind of clarifies the idea behind that. So let's take a look at the last few slides here. So big data refers to data sets so large and so complex that their analysis is beyond the capabilities of traditional software tools. Analysis of big data may require software simultaneously running in parallel on many different computers. So data science involves applications of statistics, computer science, and software engineering, along with some other relevant fields such as sociology or finance. So these last few slides are just giving you more statistics talk, for lack of better wording. Missing data, a data value is missing completely at random if the likelihood of it being missing is independent of its value or any of the other values in the data set. That is, any data value is just as likely to be missing as any other data value. Again, if it's random, if you're collecting your data randomly, then of course you can have one missing randomly. So that's kind of the idea behind that. Data value is missing not at random if this missing value is related to the reason that is missing. So we didn't get data from this one area of New York State, and so that's not missing at random. We forgot that county or something. So that's kind of the idea with that as well. I wouldn't get too nervous about some of these terms at the end though. Correcting for missing data, we can either delete the case, we can either impute a data value, so which means we just substitute one in for them, and then that looks like it's about it. So that wraps up that section. So now if you stop the video here, you can actually go on to the next one. So we're going to be getting into 1.3, which gets into collecting data, sample data. So that's going to get kind of interesting as well. So we'll see you in the next video.